going to be cold today, right? Later in the evening?
Yes. I think not today, yesterday is going to be bad.
Yes.
Yes, today is okay.
Yeah, I can.
Yeah, tonight it may be a little bit cold.
Tomorrow after the is cold.
56 is the lowest, but that's why it's okay, I guess.
Yeah, apparently that's why they didn't change the temperature.
Maybe full screen.
Yes. And you want to double click?
No, okay,
No.
it's okay.
And what do I do with this? Okay.
Click in the second screen, that's right, but you click in the good one.
Did I do okay?
Yeah, it's okay.
Yeah, I think that's what you wanted, right?
Yeah.
You have an exam on the next lecture. Right? The homework 8, that's due. I think I postponed it to. April 4th, I think. Thursday. Thursday. Term 3. No, term 2, that's 2 exams there. And I haven't decided on the questions yet, so it's everything we covered between
First midterm.
okay, officially it's everything from the start of the semester, especially functional derivative. But having said that, I will concentrate more on midterm, between midterm 1 and midterm 2.
I mean, like from homework 5 to 8.
I don't remember the numbers.
I think we did until 4 for the first exam.
That's between midterm 1 and midterm 2, saying that is reasonably clear. Because I don't remember now. And if I say something, it will be misleading. I don't want to make a mistake. And I think few things that I have jotted down, but it doesn't mean anything, is Lagrange multiplier, problem on Lagrangian. Coupled oscillators, that's what I've written down here, but those are just for my own notes. As of now, I haven't clearly thought about it so much. But so that's just the names of the topics, keywords in the syllabus. If you go to the website, those are the keywords. So, yeah. Hopefully I'll sit on it tomorrow night. Yeah. And again, 5 questions, so that's the expectation. Anything else you guys want to point out? Okay, so here we want to talk about conservation principles and symmetries. And let's begin by talking about conservation. How many conservation principles are you aware of? you often have heard conservation of energy quite early in time, so let's list them, so. Conservation of energy. So let me just write energy. Energy is a scalar, so it's one component. What else comes to your mind when you say conservation? Linear momentum, right? So that's linear momentum. Yeah. So then comes angular momentum, right? These are three components of it, so let me call it three. It's a counting system here. So that's one, and angular momentum. That's also a vector, so it has three components. That anything else comes to your mind? Hamiltonian is typically the energy itself. Good. Hamiltonian, so it is. We will see that Hamiltonian, if it is independent of time, will be interpreted as energy, but that's good. Anything else you can think of?
In the last class, like boost or something.
Yes, boost operator, that is basically. If most of this, we are going to compare it with symmetries. Often when you're moving in different frames, one, you see something else not changing, like all the physics doesn't change between two frames of systems. And what is an operator that corresponds to that? That's called a boost operator. It doesn't have a name actually, so it's absence of a name, at least you call it a boost because this is a boost transformation, right? So, and that's also a vector, so that's three. Anything else you can think of? It's a total of 10. Since I totaled it, so probably there are only this many, but can you still think of something that stays conserved? Especially when you think of. Charge. Right, charge stays conserved, right? And there are many kinds of charges. Like when you do high energy physics, if you do advanced physics, there is lepton charge, there is color charge. So there are many other things that shows up. Spin. Spin is an angular momentum. Very good. So you use the word spin, angular momentum. Angular momentum contains spin in it. When you're in the rest frame, angular momentum is defined as a spin. For example, if the way we define angular momentum is r cross p, p has velocity in it. So if you set velocity to 0, angular momentum is gone. So that means to say that if I measure my own angular momentum, it will always be 0 because velocity is 0. But it turns out that in my own rest frame, often objects have angular momentum, and intrinsic angular momentum, and that's called the spin. So angular momentum has spin. But if we restrict our attention to only these, so as I said, there are more than other conserved quantities. But if we restrict to this is called the Poincare algebra. We won't talk much about the Poincare algebra itself, just to point out that this is what is called the Poincare algebra. Exactly like rotation algebra. This is, maybe I should point out what are the transformations. I said conservation principles and symmetries, right? So these are the conservation principles, and the symmetries that you associate with it is energy is associated with a time translation. Now, to begin with, why would symmetries have anything to do with conservation? That's not very clear at all. That's what we will do. That's part of your homework also. But the main idea is, again, very counterintuitive, that is that if you have an energy of the system of this room, let's say, and you again come in the future and again ask what is the energy of the system. If it does not change in time, then you say energy is conserved, right? I should not say energy Hamiltonian, let's say Hamiltonian or the action that does not change with time. Then you would say that energy is conserved. Similarly, under translation, this was time translation, space translation, or another way of saying is if you have Hamiltonian, you have the Hamiltonian equations of motions, right? When we have Newton's equations of motion or Hamiltonian equations of motions, we don't talk about is this valid today? We don't put a date on it, right? Oh, Hamiltonian equations for today. Hamiltonian equations for 1 century before, or for that matter, go millions of years back. How are we so sure that our Newton's law are valid even at that time? Maybe there is a correction to that. Do we even know about that? So the understanding is that if Newton's laws or Hamiltonian equations are valid independent of time, like especially early universe, when things were extremely different, in that case, you would say energy is conserved. If energy is conserved, then you require your equations of motions to be true at every point in time. Translation in space. Are we sure that our Newton's laws of equations works in another galaxy, another planet, another region of space? We are not sure, but from our understanding of space and time, it seems like space translation doesn't affect your equations of motion. Here we are talking about action, Hamiltonian, and so on, and we will see what's the connection between them. What do we mean by moving moving our system from one point to the other, and how does it not change? Angular momentum is rotations in space. So rotate your system and it should not change. And boost operator is boost itself, right? That's a name is associated with that. Boost means if I'm moving, so I have a system and there is another system that is moving with uniform velocity, then does the physics change or not? Remember, it is the physics that does not have to change, some effect that leads to another effect. The interpretations should not change. So that's an observation. Like this is what we would like to understand. And our point is that based on our action principle, stationary action principle, especially the variations at the boundary, we can decipher this. We are going to Orto's neither. So this is also, so the connection between these two, that's called the Noether's theorem. That if one of these quantities is conserved, that means there must be the symmetry associated with this in the system. And it is if and only if condition, if the symmetry is there in the system, you can be sure that the system has those conservation principles in there. Okay, so that's what we would like to decipher, and your homework is mostly about these three operators. We don't go into the boost because it's a little more difficult to evaluate that, so we will go with the first three and get that. Okay. Do any questions at this stage? Okay. Yes. Change your camera. Change your camera. Thank you. Yeah, thank you. Okay. So we go back to our action principle. What we have done is this is action. Let me write the action. Last time I wrote the action in terms of the Lagrangian and got the variational principles. I want to this time write it for the Hamiltonian. Or let me begin with action in terms of Lagrangian. So that's what we did last time. Let me summarize this, and maybe on the other side of the board, I'll do the same thing for action in terms of the Hamiltonian. So this is mostly summary, but see that, I mean, it's good to have a general idea. So the action itself is an integral in time of the Lagrangian. Position T or T and T. And this we often say is as a short form, we write it as velocity. Clearly, this is an implicit time, that's an explicit time. This is implicit, and this derivative with time is interpreted as an explicit dependence on time. We made the following variations. So there are three, right? So R, T1, and T2. So say R as a function of time, make a small change, an arbitrary small change. That's an arbitrary small change that you make in the trajectory, in the possible trajectory of the system, not the trajectory itself, in the sense that it is not the trajectory that the system needs to take, any arbitrary trajectory. He also said, let's say T1 goes from T1 plus to T1 and T2, going from T2 plus to T2. And whenever you make a change in the boundary, we could actually make some substitution and bring the variation into the bulk. So let me use some language here. So by bulk, I mean between T1 and T2. So T between T1 and T2. And surface or boundary or surface, surface or boundary means at T1 and T2. So this like you have a set, so this is your T, that's your T2, that's your T1, and T is somewhere in between. So there's a bulk and there is a boundary. That's just a language, just in case there's confusion. That's pretty standard language in most of the physics we use, bulk and boundary. If I make this variation, what is the change in the action? So the change in the action we found last time is that, first of all, there is a variation in the bulk. The variation in the bulk, so that's T1, T2, that's T2. This comes out to be change in the Lagrangian with respect to R minus of d by dt of P, where P is right here. So P is equal to the partial derivative of the Lagrangian with respect to velocity plus dt variation in the bulk. So this is the time variation in the bulk here, right? So that's not a vector, so I don't know dot product. L by T and plus by T of the Hamiltonian. And the Hamiltonian is equal to P with V minus the Lagrangian. And there is one more last term that comes in. This contributes only at the boundary. So this is the term that comes at the boundary. Right. That's what is important for us today. And that's d by dt of often we say this is just g of t, where g of t is equal. Let me just write it. Well, to t with the variation delta r. And notice, since it's a total derivative, this contributes only at t1 and t2. Right, this is a boundary term. Like it's a way of writing a boundary term. This is a total derivative. It contributes only at t1 and t2. So, one conclusion you can make is if so, these are both at the boundary, right, or at the bulk. So this is our equations of motion. If action principle, like stationary action principle, states that if there is no change in the boundary, if there is no change in the boundary, then this is zero. So that means dl by dr is equal to dp by dt. That's Newton's laws. Right? That's Newton's laws of motion. If the boundary is zero, then it tells us that the partial derivative of the Lagrangian with time is nothing but the total derivative of the Hamiltonian, and Hamiltonian is the energy. So that's conservation of energy in a sense, but we will come to. And there's a minus sign. Thank you very much. Good catch. Okay, that's a minus sign. And if we are talking about a real particle going along a trajectory, these equations are valid. These two terms are zero. So for a trajectory, by trajectory, I mean for motion, right? For motion. When a particle is moving, only this contributes. So the action is not zero at the time. Action, change in the action for a moving particle is d by dt, right? This is g2, gt2 minus gt1. Because this whole thing contributes, so this is g. So that's what we have. So motion is described by variations only at the boundary, and we will talk about what are the implications of this. And this is often called the generator. Here, generator of motion in principle. So that's what we did last time. Very quickly, let me do the same thing for the Hamiltonian, so that this is sort of a summary of all the variations that we can talk about for the action. So let me quickly do this for action in terms of Hamiltonian. So think of space here. The only difference is that now we have both position and momentum as dynamical variables. So this is P with P r by dt minus of Lagrangian. Basically, this whole thing is the Hamiltonian. Okay, so you write the action to be no H, right? So H, because you want the same, right? The action cannot change. Action is a Lagrangian. Lagrangian is written in terms of the Hamiltonian in that form. Okay. Make the same
Then dr over dt is v, right?
V. Yes, yes,
So h depends on v.
yes. Sorry, that's your point, right?
Yeah.
My bad, very bad. Thank you. Yeah, that's a bad mistake. Yeah, thank you very much. Thank you for correcting. Yeah, that was simple. Correction, very good. Yeah. Hamiltonian does not depend on velocity. That's a statement. That's a very likely problem in the exam. I've asked this before, prove that Hamiltonian cannot, or by definition does not, by construction, I should say, not definition, does not depend on velocity. Okay. Here we had change only in R, so this time we can change R and P, right? So this is R plus orbit variation, any variation possible. And momentum also can change now. And T1, right? So this remains the same. T1 plus delta T1, T2 plus delta T2. And the change in the action now we'll have three variations in the bulk and one in the boundary. T1, T2, Tt. Let's start with dr. Variations that's equal to partial derivative with respect to r, and that's equal. So this is one of Hamilton's equations of motion. Derivative of momentum is the partial derivative of the Hamiltonian with position, and there are two more, right? We did not do this. In the class, we did this, right? But the expectation is that you should be able to repeat the whole process even for the Hamiltonian, and you will get these equations of motion. This is minus T plus, and the boundary variations in time penetrate n time partial derivative of the Hamiltonian with respect to time plus by T, and finally the same piece shows up here also at the boundary. Sure. T1, T2, Tt, T by dt, and here let me write T, since I've already once written in that, it's just the generator. If we are talking about stationary action principle in terms of the Hamiltonian, the first equation tells us that dt by dt. This is the second law in a sense of momentum and force and energy, right? So this is by dr. This is by dt definition of momentum or velocity, if you want. And this implies E is minus partial derivative of h time, and the generator is already there. These are called the Hamilton equations of motion, especially the first and second together. The third one also is in principle included, and these are the Lagrangian equations of motion. Usually you say it is Euler-Lagrangian equations of motion. For a trajectory or for motion, right, same thing. For motion, stationary action principle is applicable, so the first three go to zero, so only the fourth contributes, and again we have for motion The change in the action is G of T2 minus T1. And since now we are talking about for motion, the way you want to see this is that if the motion involves some symmetric form of motion, like it's going in a circle, or it is rotating, or it is just translating in time constantly, constant distances in certain time, what can we say about such a motion? So we are going to talk about motions. So motion is described by a change in action of this kind. So what will be the change in action if we choose some very specific motion? We will talk about time translation, space translation, rotations in space. Then what is a change in the action because of such simple motion, if you want. So, Okay. So let's talk about translation in space. If I move everything by 1 meter, how do I describe that? So I have to change the variables, right? So there is what is x? So x is often used as a coordinate of space, right? So that means there is a space and x, y, z represents the coordinate of space. And there was also often we say xa is position of a particle. So I don't write that a, right? Sometimes we use x as a function of time. Yes, that's a special coordinate in space. As time changes, that changes. So, right, the particle's position changes with time. That is not necessarily a coordinate. For example, electric field, right? When I say electric field as a function of r, this is coordinate in space. This is not the position of a particle. When I say in Newton's law, that I say r as a function of time, this is the position of the particle, which is one point in the whole of space. So you should be, they are very closely related, but you should differentiate. That here we are saying the coordinate in space and time. So let's say x goes to x plus, let's say epsilon 1. Y goes to y plus epsilon 2. Let me say this is delta. And z goes to z plus delta epsilon 3. That's a vector. So let me totally say that r goes to r plus delta epsilon. So the change I'm making, that's a vector. So the change, let's say this is r prime, is delta r is equal to delta epsilon. And I'm going to make this a rigid translation. By rigid translation, what I mean is that every point in space, I'm going to move the same amount. It is, I can always think of, I move this point by 5 millimeter, and this point I move by 2 millimeter, and at this point I move by 1 millimeter. That's a non-uniform translation. Right? At every point I'm choosing randomly how much I'm going to move, but suppose I move the same amount at every point, uniform translation. If you want, that's what we will call it, rigid translation. So we are talking about rigid translation, and we are going to find the change in the action because of this in two different ways. So first case I can do is I have action which is, and let me use the Hamiltonian so that it is closely related to what is there in your homework. So this helps in your homework. Most of the time in the class, I try to do it using the Lagrangian way. Same idea can be done using here. I'll do it since you have an exam coming up, so I'll do it using the Hamiltonian way. If we are doing in the Hamiltonian way, I would immediately ask, what is the change in momentum because of a translation in space? What will be the change in momentum when I move the coordinates by 1 millimeter? Is that clear? So you have a frame, you have a window where you have axis drawn, correct? You were sleeping, I moved it by 1 meter. And the question I'm asking is, will you come to know about it or not? That's about position. Yeah, you say that if it is conserved, we will derive that. But now I'm saying, what about momentum? If I move it, what's the change in momentum because of the movement of the coordinates? Zero, yeah. And why is that? That's very good. Yeah. That's correct. Very good. So the idea is momentum is velocity, right? So momentum is velocity mass times dv by dt, or sorry, dx by dt. And that's equal to m times d by dt of I'm moving, right? So let's say this is changing to x itself, or r, right? R plus delta epsilon. But this is constant in time. I'm not saying, when I say rigid, it's both position and time. So here I gave an example of change in position. It is possible that I could have thought of a translation which is different in different times. Like in the early universe, I say I translated by 0.5 millimeter, and in the recent universe, I'll translate it by half of it. That's a translation I can talk about, but I'm not doing that. So this is 0, right? So this is the same mdr by dt, and that's p. So p does not change, right? So translation, rigid translation, I'm going to define. This is my defining transformation is going to be, this changes by a constant amount, p does not change. If I'm in the Lagrangian formalism, I don't have to worry about the momentum. Right, there is only r that I'm interested in. So there I don't worry about it. But if I'm doing Hamiltonian prescription, I need to know this, and r and p, and let's say t1 comma t2 is equal to dt and p dotted with r p minus the Hamiltonian r comma p comma t. Right, that's the definition of the action. Now I'm going to make the change. So the question is, make this change and tell me what's the change in action going to be. So change in action is going to be change in action. And this is T1 to T2. So where am I making the change? Only in R, right? So this is P dotted with, wherever I see an R, I have put R itself plus delta epsilon minus of H R plus delta epsilon P and minus the action itself. Okay, that's a change in that action. Is that clear? There should have been a P plus delta P also, but P plus delta P is 0, right? That's, and here also P plus delta P will be there, but delta P is 0. So the change in action, first of all, this is 0, right? This goes to 0. So there is no change here. This minus, there is a term inside that goes to 0. So the change apparently is T1 to T2 dt, and it is minus of H R plus delta epsilon P, comma T. And there will be a term from the other side, which will be R, comma P, comma T, right? That's fine. Change. Because of this translation in space. I know how to evaluate this. That's a Taylor expansion. This minus this, how much is that equal to? Help me. How much is this? Equal to? Either. You have done this. Sorry. Okay. Point to you. Okay. So this is equal to, so remember f of what am I doing? F of x plus a minus of f of x. How much is this?
Okay.
A times the.
A times
Yeah.
Java, let's say partial, it doesn't matter because there's only one variable. So total and partial is the same. That's what it is, right? If you have R plus A minus of f of R, that's equal to A vector, and instead of this becomes a gradient. There's a dot product, that's all that happens, right? And here, P remains the same, it is mostly the changes in one variable. So I have delta epsilon, right? Instead of A, I have a delta epsilon dotted with gradient. Let me write this gradient as d by dr of h. Right? Okay. This is a constant. It can come out of the integral, right? So that's the importance of this being rigid. Like all the other variations we did was arbitrary variations. Arbitrary variations means these are dependent on time. I cannot pull them out of the integral. It was important because arbitrary variations means if it is zero, then everything has to be zero. Right? In this case, I cannot say that. So this whole thing comes out. And what I gain then is that I can bring it out. Then I can define this to be a derivative, right? Change in action. So first I bring it out of the integral. Then I can say divide it out, divide this is a vector, so it is like saying each component there is a partial derivative. This is equal to minus integral t1 to t2 dt. Right, dr. Now, if I say that the action does not change with this, so we're making a translation. I say that the action does not change with that. What can I say about the Hamiltonian? If this is not a stationary action principle, be careful. Stationary action principle is we require, that becomes a law, Newton's laws, right? We don't, now this is maybe possible, maybe not. Like certain system will be having translation symmetry, certain systems do not. So there is an if condition there. If there is a translation symmetry in the action, that means this doesn't change. Right? If the action does not change with this, so this is zero. If this is zero, the right hand side has to be zero. How can you have the right hand side to be zero? This is a sum of a lot of quantities. So each quantity has to be zero. If x plus y plus z is zero, and they are all arbitrary, then x has to be 0, y has to be 0, z has to be 0. So if this is 0, that has to be 0, right? So if, again, this, see the statement, if the action is having translation symmetry, then the partial derivative of h with respect to position has to be 0. So Hamiltonian has to have a symmetry in space. Right? That's a statement. But still there is no conservation principle showing up here. Right? So the only thing I have stated here is that if action is independent of epsilon, then the partial derivative will be 0. Then Hamiltonian is independent of position. Give me an example of a Hamiltonian that does not have position in it. Think of motion, kinetic energy, potential energy. Give me a system which does not have position in it. And give me an example of a Hamiltonian which does not have position.
Wouldn't Schrodinger's equation dependent on time?
Time dependent, but I'm saying I don't want it to be position dependent. Yeah, think of a Hamiltonian, any system. Which system will not have position in it? So there is kinetic energy and potential energy. So think of a particle which does not depend on position. Energy does not depend on position. Huh?
Like charge.
Charge in an electric field will depend on the electric field's positions, right? Or yeah, it is E times X, energy is E times electric field times. Simpler, make it this. What's the simplest system you can think of? When you do energy, the Hamiltonian or the quantum mechanics, what's the first problem that you do in quantum mechanics in some form? Like, it depends on the textbook. What's the very first problem you do? Before that, you have potential well, particle in a potential well, that's complicated. That's a simpler problem. Free particle, right? Or particle in an infinite box, right? Particle in a box will be potential in a well. Like free particle, right? There is no potential energy. What does the kinetic energy depend on? P square over 2m, only P, there is no position. A free particle doesn't care for where you are, right? It's just moving freely.
And this
Right?
kind of also shows scattering.
Yeah, it will be scattering, exactly. So it will have scattering states. Those are conclusions. But I'm saying a free particle, if in the universe there is one particle, that's it, the whole very isolated system, very lonely system, but there is only one particle in the universe. It doesn't matter whether I keep the particle here or there. There is nothing else. There is no reference. There is no table. Like I don't have a reference. So I don't have an origin there. So it doesn't matter where I keep it, its energy is the same. Right? When we say we go up, there is height h because there is a surface of Earth there. There is a reference. If it's a free particle, there is no reference. If there is no reference, there is no position dependence. So Hamiltonian for that particle, for a free particle, will be independent of position. So that's 0. Right? If the Hamiltonian is independent of the position, is it translationally symmetric? Yes, we just now said that it is translationally symmetric. No reference to linear momentum though. Where is linear momentum coming from? Right, we said that if this is going to be translationally symmetric, linear momentum will be conserved. That's the next step. Right? But for now, what we have said is that if the Hamiltonian does not have position in it, and there are lots of systems we can talk about where it will be position independent. A particle in a magnetic field with uniform, no, that has position dependence. We can talk about more position dependent Hamiltonians. In that case, this will be equal to 0 because this is 0, that's equal to 0. So it is one way or the other.
If we consider that statement, like if action is independent of that one, can't we substitute dou H by dou R is equal to dP by dt?
This is already, yes, we can. So, oh yeah, so that is how you will come up with, you want to use the momentum. So you are going ahead and you're saying that, oh, where is the momentum coming in? Yes, that is how you would go about it. But I want to, like, that is surely one way, but I want to look at it from the generator point of view. I want to see this as a change in boundary. For momentum, it is easy to see it that way. The time translation, it will be harder to see it that way. You're one step ahead of me. That's exactly how you would proceed and see this momentum also. Very good. Very good. Which is there in Newton's law itself. dP by dt is equal to rate of change of Hamiltonian or gradient of the Hamiltonian. If the Hamiltonian is position dependent, then momentum is conserved. Very good. So you see the whole point. But if you missed whatever Dilipshi pointed out, so I'll talk about that and few minutes. Okay, so that's your first statement about the translation. But now let's go and do another way. We also know how to change the action. You're talking about motion. It is also given by change in action is equal to, let me write instead of GT2 and GT1, let me write this as a total derivative. Then I don't have to write it only once. That's P with dr minus H delta T. Right? That we have already done, which again, just now Dilakshi pointed out that, oh, I can see that in another way. Those are all true statements. And this is equal to, now for rigid translation, this is T1, T2, T, that's T dotted with delta epsilon and minus 0. Delta T is, oh, I should say translation one more thing, right? Delta T. I didn't say anything about time. I should define my rigid translation as time being, change in time being 0 and change in position being a constant. This is a constant, I can bring it out again. So this is delta epsilon dotted with T1, T2, dt, dp by dt. So we again learn this is T1 to T2 dt dp by dt, which is the same as P of T2 minus P of T1. And that's what Dilakshi was pointing out, that I can use equations of motion right here and arrive at this point. But now we have arrived at this point using the variations at the boundary. This one was variation in the bulk. We are keeping the boundary the same and coming at the same statement. Two independent statements, but now I can connect them, right? So if this is equal to 0, Hamiltonian is independent of the position. If the Hamiltonian is independent of the position, that's 0, but already action is independent of the rigid translation. So this has to be equal to 0. So if the action is independent of translation. So if this is equal to 0, so this implies that the Hamiltonian is independent of position, and this implies that momentum is conserved. Let me write that as dp by dt is equal to 0. Right. So that's, and this is stylus here, like a very simple statement, but you wouldn't have expected that translation and this will be connected, especially for energy where it is a time dependent variation that comes out non-trivial. Okay. Do the same thing for translation, or let me do rotation. Let's do rigid rotation. Maybe I should say rigid infinitesimal rotation. That should also be infinitesimal, right? So I made a small rotation. So sorry, translation. So this is infinity. This is signal rotation. Infinitesimal rotations are described by R prime is equal to R plus delta R. And often you will see sometimes I write this as plus delta R and minus delta R. That depends on whether it is an active transformation or a passive transformation. By active and passive transformation, what we mean is that you can, when I rotate a system, I can keep the particles same and change the axis. Right, so axis is changing, particle remains the same. This is passive transformation. Another way of looking at it is you move the particle itself. Right, under a rotation, the particle moves from one point to the other, that's active. So the object itself is rotating, you keep the coordinate system the same and you move the particle. So, and accordingly, one will have a plus and minus sign in them. For rotations, delta R, for rigid rotations, delta R is equal to a small infinitely tiny rotation, so that's delta theta crossed with R. How do you want to interpret this? We always say if we were to divide this by time, this is nothing but V is equal to omega crossed with R. Is that a familiar equation? Right, that's in mechanics, a familiar equation. Tell me what's the, if I'm going in a circle, that's my R. Velocity is always tangential to the trajectory. That's the velocity. Where is omega? Right, it is coming out of the boat, so omega is, that's the direction of omega. Clear? So you use your right hand rule, and often the curl gives you the direction of velocity, or use your right hand rule, however you want to use it, the cross product idea, right? Omega is coming along the axis. Clear? Delta theta, so omega is rate of change of angle with time, right? So this is d theta over dt. The direction is contained in d theta. What's the direction of d theta? It will be coming out. dt doesn't have any direction. The velocity gets its direction from the displacement, right? This is the angular displacement. So the interpretation of delta theta is in rotation. Right? This is the direction of delta theta is the axis of rotation. Any rotation, any infinitely tiny rotation we are talking about, any infinitely tiny rotation, you think of an axis and a tiny rotation around it. That's it. So there are three. If you want to specify the rotation, you need information about three: a direction and a magnitude, and that's delta theta is the amount of rotation. Is the amount of rotation. That's not how we usually do it in rotation, rectangular coordinates. Rectangular coordinates, we say we rotate about x-axis, we rotate about y-axis, we rotate about z-axis. That's a very generic way of doing it in rectangular coordinates. This is the geometric way of looking at it, very powerful. Direction is the axis of rotation. Delta theta is the magnitude of rotation. That's it. Right? So if you want, this need not be the x-axis. So if I'm rotating around this direction, right, get me the direction of n hat, and the amount of rotation you make is delta theta. So d theta is equal to n hat times delta theta. Okay, that's it. We're done with it. All the x, y, z rotations is contained in your n hat. So there's a lot of simplification, geometrically speaking, much more powerful than your x, y, z, which is very tedious. You find the rotation about x-axis, then find the rotation about y-axis, and rotations are not commutative. Is that familiar idea? Rotation is not commutative. Often you say this using the following way. Maybe I think I've told this before also, but you should all know this. So let's say we have a remote in this form. It is facing the camera, right? So remember this position of the remote. And I'm going to do 2 rotations, one about x-axis and one about y-axis, or let's say shot with z, right? So I'm going to do 90-degree rotation. So that's a remember the orientation. I'm doing it this way. You'll need to help me with this. Yeah. So first do this rotation, and then let me rotate it this way. Okay. So first one was this way, and the second one was along this line. Right? So basically this way. So first rotation, second rotation. I'm going to do the second rotation first now, right? So that will be this. Correct. This one, and then you do this. Right, notice now where is my final position? This remote is facing the camera. Earlier I did this, and this it is facing you. So rotation, the order of rotation does not lead you to the same place. Even if you do this at an infinitely tiny amount, it does not lead you to the same place. Okay, this is what you see as commutation relations of angular momentum in quantum mechanics. That's the same idea. Okay. So you have to take care of one of those. That's good to be aware of. But for our purposes, change in position of a particle under rotations is described by this. In my way, in the Hamiltonian way of doing it, we also need to know what is momentum. How does momentum change under rotation? Linear momentum, yeah. Linear momentum, how does it change under rotation? So like I'm defining my rotational transformation, right? I have to say that, oh, okay, under translation, position goes this way. Momentum does not go, I argued, right? So similarly, how do I know how momentum transforms under rotation? The standard classical momentum. Okay, velocity, how does velocity transform under rotations. Like position x, y, z, we go to x prime, y prime, z prime, and write cosine theta, sine theta, and so on. What about velocity? How would that change? The general statement is under if this is how a vector is defined. How something moves under rotation is the definition of a vector. So vector goes to change in R under rotations. Momentum is also a vector, right? So it also has to have the same relation. We'll talk about this a little bit more, about why we do, there is no why, I mean, that's how we define a vector. Sorry, this is P. Any vector, right? P going to delta P.
Wouldn't that be d omega, not d theta?
No, this is just omega. This is delta, if this is the case. You can always, if I divide it by time, so what you're thinking probably is dp by dt. If I want, that will be, I'll put a divide by time, that will be omega crossed with p. We don't write it often in elementary introductory physics, but that's a relation. Take any other vector, think of another vector in introductory physics. Another vector in introductory physics, angular momentum is a vector, right? How does it transform under rotation? L crossed with delta theta is delta L. Any vector transforms like that. If you were to really put it in, do it from the scratch, will always come out to be that. In fact, that's a definition of a vector. Like at some stage, you say that's a definition of a vector. How do you define a vector by?
It's unit vectors.
Yeah, but how will you define a vector? Huh? Yeah, that's at some stage. Like anything that has a magnitude and the direction is a little vague, right? So if you somewhere go into the basic textbooks, like of course I also teach it the same way, magnitude and direction, introductory level physics, but somewhere at 300 level, 400 level, we start talking about what is a vector, what is a tensor, and so on. So usually there is a transformation associated with it. You see this in relativity, special relativity. What is a 4 vector?
So position, between
Position and time, something that transforms like a Lorentz vector, like under Lorentz transformation, if there is if certain 4 components transform in a certain way, that's a 4 vector. So give me a transformation. A 4 vector goes that way, that is how you define a vector. A vector is always associated with a transformation. Like this is a vector under rotation. Later we will tell a vector, a 4 vector under Lorentz transformation. You can talk about general transformation. A vector in general transformation. That's general relativity. So a vector is always associated with the transformations. But for our purposes, let's stick to this. For our purposes, we just need this information. This is all to motivate the fact that why this is the case. What about delta G? Is 0, right? Under rotations, time doesn't come into picture at all. That's equal to 0. Go back in the first statement now. What is a change in action? So change in action is equal to T1, T2, dt, and this is a change. So let me, this is P plus delta P dotted with d by dt of R plus delta R, where delta R is this, delta P is this minus of the Hamiltonian going from R to R plus delta R P P plus delta P and time. And the whole thing subtracted out minus the action. Okay. When I subtract things out, I have a delta P. Dotted with dr by dt plus P dotted with by dt of delta R minus of H plus H of the thing. I just subtracted various things, and let me quickly do this. Oh, only a few minutes. Okay. Delta P is delta theta crossed with P dotted with the R by dt plus P dotted with dt delta theta cross with R. This is minus delta R dotted with delta theta cross with R dotted with dh by dr minus delta theta cross with P dotted with dh by dp. Okay. I'm just substituting. Now, one more step. Cross and dot can be interchanged in a vector product. A cross B cross C is A dotted with B cross C. So this is delta theta dotted with P crossed with dr by dt. So that's basically using A cross B dotted with C is equal to A dotted with B crossed with C. I think the brackets parenthesis is not important because first you have to take the cross product. In this case, delta theta again rigid means that this is independent of time, independent of position. You can think of a rotation where at every time I make different rotations. So if it is time independent, I can move this out, move the P on the other side, and this is the same as delta theta dotted with dr by dt crossed with P. Like I move this delta theta out, P by dt only hits the R. Move the P on the other side, and that's equal to this. What's the first and second term together equal to? Together? Yeah, I heard that. 0, and why is that? Good.
You can substitute.
A cross B, right? The vector product is A cross B.
Is minus because.
Very good. Right, A cross B is minus B cross A. Right, so these two are negative of each other, so that goes away. And this one is nothing but minus delta theta dotted with R cross with partial derivative of R and plus P cross with dh by dp. So this goes away. So I have, and delta theta can come out. So what I learned here is that jumping a couple of steps, just not going slow, that's all. This is time t1 to t2, dt, R cross P. So again, go back to our argument. Here we had a nice interpretation of the translation. If the action is independent of the translation parameter, then the Hamiltonian has to be independent of R, right? Now, what does this mean? What is this meaning? Right, that seems to be a cross product. So we go back here and we should ask, what is this meaning? Okay, so this could be any function like any Hamiltonian. If this is equal to 0, what can I say? What does that mean? Go to spherical coordinates. So what that means is, this is in spherical coordinates, what is vector R? Spherical coordinates, what is vector R? The unit vector is R hat times R itself, magnitude direction, it's straightforward. So it is, so this means it is R hat. And what is gradient? This is gradient, correct? So gradient operator in spherical coordinates is R hat d by dr plus theta hat 1 over R sine theta. Very good, d by d theta plus phi hat. No, there's a mistake.
This is all over us.
1 over R. Okay. This is 1 over R d by d theta, no sine theta there, and phi hat
All over.
1.
One of ours.
Very good, right? That's d phi of Hamiltonian. This is equal to 0. So we are saying, what does this mean? R hat crossed with R hat is 0. So this term is gone. So R is not equal to 0. So what I have is that R crossed with theta hat, R hat crossed with theta hat times 1 by R dh by d theta plus R hat crossed with phi hat 1 over R sine theta dh by d phi is equal to 0. R hat crossed with theta hat, R cancels out, you can remove the R, good. R cancels out with that also, that's good. Cancel that, and the second time I was canceling, good. So that's equal to 0. R hat crossed with phi hat, theta hat is phi hat. Okay, with some probably, no, this is phi hat, this is perfectly okay. And R hat crossed with phi hat is R sine theta, sorry, theta sine theta. This is theta hat, sine theta cancels out, and that's dh by d phi. R hat crossed with, that's minus theta hat, thank you, very good. Right, very good. So that's equal to 0. So what, again, what are we asking? What does this mean? Right? If this is equal to 0, this is equal to 0. This is a vector, its components has to be 0. So that's theta is equal to 0. And dh by d phi is equal to 0. Right? So that means the Hamiltonian, which could have R theta phi in general, does not have theta, does not have phi. Which is what we understand when there is spherical symmetry. There's no theta, there is no phi. So this means spherical symmetry. Hamiltonians that have spherical symmetry are called central or forces that correspond to Hamiltonians that have spherical symmetry are called central forces. Newton's gravity is a central force. I should stop here. You guys tolerate me. Well, yeah. I'll stop here. Thanks. So, oh, there's one more step here that I have to show. Angular momentum is conserved. That's in your homework. Okay, so this is a mostly part of the homework. So you will see it in the homework. So there's one more step here that dl by dt is equal to 0. Right, here we have 3 steps, right? I have done until here. So you don't have to show that angular momentum is really conserved, but in your homework, that comes out very cleanly. So I'm gonna jump that. Okay, thank you.